We choose to go to the moon in this decade and do the other things. Not because they are easy, but because they are hard.
Godspeed, John Glenn.
Roger, 0G, and I feel fine.
Get my feet up. Okay, I'm out.
How does it feel for the United States to be the new record holder?
At last, huh?
When that baby lights, there's no doubt about it.
Liftoff. We have a liftoff. 32 minutes past the hour. Liftoff on Apollo 11.
Houston, Tranquility Base here. The Eagle has landed.
That's one small step for man, one giant leap for mankind.
Hello and welcome. This is Michael Annis, and you're listening to episode 120 of the Space Rocket History Podcast. And now, Apollo stages, S4 and S-IVB. No study of Apollo would be complete without covering the Saturn rocket stages that propelled mankind to the moon. We've already spent some time on the first stage of the Saturn I, so today I want to cover the second stage of the Saturn I, called the S4, and its descendant, the S-IVB. The S4 stage will evolve into the S-IVB, which was used as the second stage of the Saturn 1B and the third stage of the Saturn V. Both the S4 and the S-IVB used liquid hydrogen and liquid oxygen as propellants. They shared the same basic design, concepts, and manufacturing techniques, and were manufactured by the Douglas Aircraft Company. The key difference in the versions was the S4 used a cluster of 6 RL-10 engines, but the S-IVB used a single J2 engine, and it had a larger diameter. If I have confused you, there's a picture available on the website that will make everything crystal clear. Now let's consider what made the S4 special over previous liquid-fueled rockets. Up until this time, nearly all of the liquid oxygen kerosene boosters in use when the Saturn program began reflected a direct lineage from the ballistic missiles of the 1950s. The Thor performed service for unmanned satellites and probes, and the Atlas and the Titan operated successfully through the Mercury and Gemini programs. But these boosters had not been designed for such missions, nor were they capable of orbiting the manned payloads expected in the Saturn program. For these reasons, a unique, staged, large payload-oriented launch vehicle was needed. The upper stages of such a vehicle were critical to the eventual success of the mission, especially the top stage, which inserted the payload into the final stabilized orbit. The overall performance of the last stage had a greater influence than the primary stages. The Saturn V launch vehicle for the lunar mission required 50 pounds of booster weight at liftoff for every 1 pound of payload injected into a translunar trajectory. Without high-energy upper stages, this factor would be significantly greater. Now, the most important point of the episode. The key to high-energy stages was the use of liquid hydrogen as the fuel. Liquid hydrogen fuel appealed to rocket designers because of its high specific impulse, which is a basic measure of rocket performance. Specific impulse is the impulse delivered per unit of propellant consumed. You might think about it as the efficiency of the rocket. Compared to an RP-1 kerosene-fueled engine of similar size, liquid hydrogen fuel could increase the specific impulse or efficiency of that engine by 40%. The combination of hydrogen and oxygen for propellants made the moonshot feasible. Its use in upper stages resulted in a significant increase in performance over the propellant combinations of oxygen and kerosene, which was then in use in first stage boosters. So the S-4 and the S-4B would use liquid hydrogen. Many aspects of the S-4 design were transferred directly to the S-4B, even though the S-4B used only one engine instead of a cluster of 6. The configurations of both upper stages depended on the mission requirement and ultimately on the location of the stages in various Saturn vehicles. Originally, Douglas planned a 5.6 meter diameter stage for S-4B when it was designed for the Earth orbit rendezvous mode. As you may recall, the Earth orbit rendezvous mode could require a coast in low Earth orbit for as long as 30 days, which permitted time for subsequent launches of other Saturn and Apollo hardware, rendezvous, and preparation for injection into lunar transfer orbit. As the mission profile changed from Earth orbit rendezvous to lunar orbit rendezvous, the S-4B design requirements shifted to a 4.5-hour coast in low Earth orbit, followed by a translunar injection burn and a 2-hour period in translunar coast. Douglas eventually received a design change notice to go from a 5.6 meter version to a 6.6 meter tank. The reason for the change related to the mission of the interim Saturn 1B, and the increased diameter allowed added payload for capability for launching and testing Apollo components in Earth orbit. The increased S-4B capability was also compatible with its ultimate role in Saturn V as envisioned at Marshall Space Flight Center. By 1964, the details were fairly determined. In the mission, the S-4B had 2 critical responsibilities: get the Apollo craft into orbit, then restart and insert the payload into the translunar trajectory. The orbital phase left the S-4B instrument unit and Apollo spacecraft in an Earth orbit of 185 kilometers, where they remained for about 4.5 hours, or time for 3 orbits of the Earth. Following the powered flight, which consumed about half of the propellant, the stage relied on its auxiliary propulsion system during the orbital coast to ensure proper attitude control and ullage orientation of the remaining propellants toward the bottom of the tank prior to engine restart. Remember, ullage is an old brewmaster's term that referred to the volume of air above a particularly full container. After restart, the second burn put the S-4B and Apollo spacecraft into the translunar trajectory and consumed the remainder of the propellant. With burnout of the S-4B verified, the transposition maneuver was carried out, which was a nose-to-nose rendezvous of the lunar module and the command service module. Concluding this maneuver, the spent S-4B and instrument unit were separated from the lunar module command service module by retrofire ordnance aboard S-4B, and the mission of the Saturn V third stage was over. Now some design considerations. The nature of the S-4B mission imposed special requirements on its design. For one thing, the engine and stage needed the capability to restart in orbit. The stage had to have special equipment to ensure storage of propellants and proper orientation while in Earth orbit for 4 to 5 hours. Although the S-4 relied on 6 RL-10 liquid hydrogen engines, and the S-4B mounted only one J-2, the choice of propellants remained the same: The S-4B carried more propellant for a longer time, and the mission of the Saturn V, calling for restart in orbit, imposed some new design requirements. For example, stage interfaces in different Saturn vehicles required different skirts and interstage designs. The stages, however, were essentially the same. The delivery of the first S-4B flight stage to NASA in 1965 was the culmination of a single thread of the story of the design, fabrication, and manufacture of the S-4 and the S-4B liquid hydrogen upper stages. Now some thoughts on fabrication and manufacturing. Douglas was fortunate in being able to draw on the Thor rocket experience for the more advanced S-4 and S-4B. It began with the tank skins and carried into many related fabrication and production techniques, including metal removal by machining and by chemical milling, forming by stretching and bending, welding, chemical bonding, and mechanical fastening. When the Thor project entered the phase of design studies back in the mid-50s, engineers screened a number of metallurgical candidates for the rocket's propellant tanks. With its heritage of advanced aircraft design and production, Douglas had considerable experience in handling various aluminum alloys. These metals and other nominees were therefore subjected to extensive test and analysis for use as cryogenic tankage. Adaptability for fabrication and inspection requirements for quality assurance were included in the test. The Thor tanks not only had to be amiable to cryogenics with liquid oxygen, but the tanks also had to be weldable. Welded joints promised the only sure way to control leaks of the cryogenic fuels. As it turns out, cryogenic leaks had a high potential for explosion, so they had to be contained. When testing, it was determined that the 2014 aluminum alloy selected for the Thor worked so well that Douglas chose it for the S-4 and continued its use in the S-4B. During the Thor design program, engineers considered several fabrication methods for tanks, including conventional skin and stringer designs, as well as monocoque style derived from aircraft construction. Both were rejected because of drawbacks of weight and construction requirements. With a design goal for very thin but rigid walls, Douglas finally settled on an integrally stiffened shell structure using special equipment to literally carve out ribs from the inside walls of the tanks. The waffle-like pattern that resulted was both practical and efficient. The waffle recesses were about 7.5 centimeters square, bounded by ribs that increased the buckling strength of the tank walls. The S-4 and S-4B featured the same waffle-shaped integral stiffening for their liquid hydrogen tanks, although designers increased the waffle size and the S-4 skins were milled from 1.3 centimeter plates as compared with 1.9 centimeter plates used for the S-4B. Moving on to the tank domes. For the S-4 and S-4B, Douglas settled on a true hemispherical shape. This design meant that the domes were deeper and increased the overall weight of the stage. Douglas accepted this penalty in exchange for the extra strength inherent in the design, the possibility of a smaller diameter for the stage, and the resulting simplicity in tooling. Like the Centaur booster, the S-4 and S-4B relied on a common bulkhead to separate the fuel from the oxidizer. In more conventional designs, the propellants were housed in separate tanks, each with its own forward and aft domes and tank walls. The common bulkhead method in the case of the S4 and S-IVB meant a reduction in structural weight of up to 20%. Douglas developed a double-faced hemispherical structure about 5 centimeters thick with a pair of 2014 T6 aluminum shells on either side of a fiberglass honeycomb core. The bulkhead separated liquid hydrogen at minus 250 degrees C on one side from liquid oxygen at minus 172 degrees C on the other side. The common bulkhead served as an end dome for both liquid hydrogen and liquid oxygen tanks, as well as insulation to prevent heat flow from the liquid oxygen to the colder liquid hydrogen. Otherwise, the liquid oxygen would freeze solid. The bulkhead was designed to take the thermal stresses and reverse pressures as well as to survive a major loss of pressure from either side. For the aluminum structural assemblies of the S-IVB, Douglas relied on conventional designs, fabrication, and manufacturing development from its experience as an airframe manufacturer. Details of the assemblies for the forward skirt, aft skirt, inner stage, and thrust structure were produced by numerically controlled equipment with panels riveted together in automatic machines. The forward and aft skirts included fittings to support assorted electrical and mechanical subsystems and vents, as well as propellant lines and umbilical connections required for operations at the launch site. The aft skirt carried the auxiliary propulsion system modules, and the aft inner stage contained fittings for the retro rockets. The thrust structure featured skin and stringer construction for strength and rigidity. It contained several access panels and carried attach angles for miscellaneous engine fittings and other equipment. The bottom of the thrust structure carried the fitting for the engine mount and was machined on a numerically controlled vertical turret lathe and a 5-axis milling machine. The assembly of the complete vehicle in one of the assembly and welding towers involved the joining of the complete liquid oxygen tank and liquid hydrogen cylinder. The steps to accomplish the task were complex, requiring both inside and outside welding with the stage in upright as well as inverted positions. The tank assembly techniques relied on many special maneuvers as well as special care in welding. During these final sequences, careful X-ray tests and a permanent die check were performed to search for invisible structural inconsistencies, ending with verification of the structural integrity of the complete liquid hydrogen, liquid oxygen tank assembly. The decision to use liquid hydrogen in the upper tank presented designers with a formidable insulation problem. After much deliberation and study, the decision was made to install insulation inside the tank as opposed to externally. This special installation process required a considerable amount of individual fitting by hand, and a search for the proper insulation materials absorbed many months of time and effort. After conducting tests of a number of potential materials, Douglas technicians finally devised their own insulation. To form workable masses of insulation material, they contrived a 3-dimensional matrix of fiberglass threads woven into a box-like form. After it was strung, the matrix frame was placed in a mold and polyurethane foam was poured in and cured. The result was a reinforced foam block 30 centimeters square and 20 centimeters deep, which could then be sawed into a pile of flat plaques, then machined to the required convex and concave contours appropriate for the interior of the S4 liquid hydrogen tank. The recessed waffle pattern construction of the tank's interior required special attention in shaping each tile to fit. Using a machine tool with custom fixtures and cutters, operators recessed edges and cut steps on each tile. The tile then slipped into the appropriate indentation in the waffle pattern and still covered the notched step cut of each adjoining tile for a smooth surface. The waffle pattern included some variations in design requiring each of the 4,300 tiles to be numbered and individually shaped to its unique position inside the tank. In cutting the tiles, Douglas discovered a true case of serendipity. The saw cuts left small ends of fiberglass thread sticking out around the edges, which served admirably to engage the adhesive as each tile was installed. Now a word about the propulsion system. The use of liquid hydrogen necessitated some new techniques, and the differences in upper stages introduced additional design variations. The ubiquitous S-IVB upper stage, sharing the J2 power plant with the S2 stage, exemplified the nature of stage systems required for Saturn vehicle missions, particularly the Saturn V. Saturn V's S-IVB included 6 basic systems: propulsion, flight control, electrical power, instrumentation and telemetry, environmental control, and ordnance. Effective operation of the J2 engine depended on the ability of the S-IVB to manage the supply of liquid oxygen and liquid hydrogen on board. The propulsion system included not only the J2 engine, but also the propellant supply system, a pneumatic control system, and a propellant utilization system. With 2 kinds of propellant aboard a liquid-propelled rocket, designers wanted both tanks to run dry at the same time, so as not to compromise mission performance. The propellant utilization system function was to assure simultaneous depletion of propellants by controlling the liquid oxygen flow rate of the J2 engine. This was required to prevent residual amounts of fuel left in either of the tanks that would subtract from the accuracy and stability of a desired trajectory or orbit. The flight control system gave the S-IVB stage its attitude control and thrust vector steering from correction signals originating in the instrument unit. The vehicle was steered by hydraulic actuator assemblies that gimbaled the J2 engine. To prevent damage to the engine during liftoff, boost, and stage separation, the instrument unit commanded the actuators to keep the engine in the null position and repeated this function prior to reignition sequence. Although the stage was completely programmed for automatic operation, ground observers monitored its operation from start to finish via the telemetry and instrumentation system. The stage carried 1 transmitter using 2 antennas. During staging, some of the data was lost in transmission, and similar losses occurred during parts of the low Earth orbit. To acquire as much information as possible during each mission, the S-IVB carried a digital data acquisition system that recorded sample data pertaining to the stage operation, then played it back when in range of ground stations. And now we will move on to the final item I want to cover today, and that is testing. No Saturn launch vehicle was ever lost during a flight mission. The phenomenal success of the Saturn program probably owed most to the two basic philosophies. First, the stringent reliability and quality assurance programs during manufacture, and two, exhaustive ground testing. Each stage required its own testing program tailored to the mission objectives and characteristics of the stage itself. Overall, the test days of the Saturn program accounted for as much as 50% of the total effort in terms of allotted man-hours and physical resources. This high figure reflected the intensity of the effort to reduce risk inherent in the manned Apollo space program. In general, the respective Saturn stages progressed through three major test phases: ground test, static firing, and demonstration flight test. In the case of the S-4 and S-4B, 5 different test configurations of the stages verified the manufacturing sequences as well as the overall design. The static test took place at Douglas's own Sacramento Test Operations, and that was pronounced SACTO. One of the ticklish problems of working with large rocket stages filled with liquid hydrogen concerned the danger of hydrogen leaks. As one authority on the rocket fuel wrote, quote, "All sorts of precautions have to be taken to make sure that oxygen doesn't get into the stuff, freeze, and produce an extremely touchy explosive," end quote. There was an added dangerous characteristic about leaks that produced hydrogen fires in daylight. The flame was invisible. So, it was possible to inadvertently blunder into the searing flame. As Harold Felix, who managed SACTO operations in the late 1960s, put it, quote, "You don't want to go into a countdown of firing if you've got leaks. It's a good way to blow up the stages," end quote. But how to detect an invisible fire? Douglas used infrared TV cameras, but they still did not provide visibility at every angle. Just to make certain, SACTO had a special examination crew outfitted with protective clothing and equipped with brooms. The men walked down the stage from the top scaffolding to the bottom, extending their brooms ahead of them. If the broom suddenly sprouted into flame, the men knew they had discovered a hydrogen leak. Still, accidents could happen, even if extra precaution was taken. During testing, there was one catastrophic failure. In a countdown for the test firing of an S-4 at SACTO on January 24, 1964, the vehicle exploded and burned. The incident at SACTO was carefully scrutinized. W.R. Lucas and J.B. Gale, both from Marshall, headed the investigating team of 11 members from Douglas and NASA. They traced the cause to an overpressurized liquid oxygen tank. At the time of the accident, tape records showed the pressure to be considerably above the design limits of the S-4 tank. Watching films taken during the test sequence, the investigators spotted a rupture in the peripheral area of the common bulkhead and the nearly instantaneous flash of the explosion. The liquid hydrogen tank, in all probability, was ruptured within milliseconds of the liquid oxygen tank break. Previously, engineers had possessed no real data on the TNT equivalent of liquid oxygen, liquid hydrogen explosions. The examination by Lucas and Gale's team had special significance for its acquisition of hard data, useful in future design of test sites and installations for maximum safety. The first flight test of the S-4 stage came on January 29, 1964, on the SA-5 flight that I covered on episode 115. Here's an audio clip on the S-4 stage's performance on that flight.
December 1963, Cape Kennedy, Florida. On Launch Pad 37B, preparations are underway for the first launch of a Saturn I vehicle employing a live second stage. This second stage, designated S-4, was designed and manufactured by the Douglas Aircraft Company. The primary objective of this mission is to flight test the Saturn I vehicle, which consists of an S-1 first stage and an S-4 second stage. For the S-4 stage, the major objectives are to achieve separation from the S-1 stage, to effect in-flight ignition of liquid hydrogen-fueled engines, to achieve engine operation until fuel depletion, and to place in the desired orbit the spent S-4 stage and the payload. The design of the S-4 stage and its operational systems, while based upon proven engineering concepts, required considerable pioneering. Several unique features are incorporated in the S-4 airframe, which must support the weight of its own 100,000 pounds of cryogenic propellants, plus the weight of the instrumentation unit and payload. April 1963, Santa Monica, California. The first S-4 flight stage, designated S-4-5, completed manufacture and system checks and was ready for acceptance firing tests. Swathed in its protective nylon cover, in the quiet pre-dawn hours, the stage was transported to the Los Angeles harbor, where it began the 400-mile voyage to the Sacramento test site. May 21st, after final hardware fitting, S-4-5 was installed in the test stand. The Saturn test stands had been provided with steam ejector blowdown systems to simulate engine operation in the vacuum of space. Because of an intensive testing program on the battleship tanks and with other test vehicles, loading of the cryogenic propellants was accomplished without incident. On the 12th of August, the full duration acceptance test was accomplished. During the test, all stage subsystems performed satisfactorily. The firing continued to a commanded cutoff. Residual fuel was less than 0.5%. All test objectives had been met, and NASA approved the test as a satisfactory acceptance firing. Following post-flight checkout, S-4-5 was taken to nearby Mather Air Force Base and loaded aboard a modified transport aircraft. September 20th. The S-4-5 stage was flown to the Atlantic Missile Range. The next day, the stage was unloaded and taken to the Special Assembly Building. For the next 19 days, S-4-5 underwent a series of system tests and the final weight and balance checks. October 10th, Launch Pad 37B. The stage was hoisted into the stand and positioned atop the waiting S-1 booster. The instrumentation unit was then positioned atop the S-4 forward interstage. This unit, weighing approximately 5,000 pounds, contained the Saturn vehicle's guidance and control package. The payload compartment was a modified Jupiter nose cone ballasted to weigh approximately 18,000 pounds. These three sections, the S-4 stage, the instrumentation unit, and the payload, would not be separated, but would go into orbit as a single unit, weighing a total of 19.5 tons, 38,685 pounds. During the following weeks, the Saturn vehicle was given a comprehensive series of integrated checks. By late January 1964, all retrofitting had been accomplished on the booster stage, and the vehicle was ready for launch. Countdown was begun on January 28. The count proceeded to launch, which was accomplished on January 29 at 11:25 a.m. Eastern Standard Time. Operation of the booster stage was nominal. First stage burning time was as planned. The S-4 engine chill-down operation, which was begun prior to separation, was successfully accomplished. At first stage engine burnout, the S-4 ullage rockets ignited, all enabling events were accomplished, and a successful separation was achieved. After separation, ignition of all 6 S4 engines occurred as planned. Thrust levels were estimated to be nominal. Ignition and operation of the helium heater was satisfactory throughout the flight. The spent ullage rockets were jettisoned as planned. Step pressurization of the liquid hydrogen tank was accomplished. During the flight, operation of the S4 telemetry system was satisfactory. Propellants were depleted as planned, and engine cutoff was accomplished as planned. Propellant utilization was estimated to be close to 100%. Operation of the flight control system was satisfactory throughout the flight, and at engine cutoff, the flight path was very close to nominal. The vehicle-payload combination went into an orbit having an apogee of 425 nautical miles and a perigee of 142 nautical miles.
In comparing the S4 to the S-4B, there was a strong consensus among those who worked on both that the more advanced S-4B was nevertheless simpler. The earlier upper stage, with its cluster of 6 engines, created more design tangles than the single S-4B, even though the latter had to have the capability to restart in space. Some of the instrumentation for the S-4B was more sophisticated, but aside from the engine, there were no major differences between the two. The electronics, including the circuitry and design for the propellant utilization probe, for example, passed easily from the S4 to the S-4B. Thanks for listening to this archive episode of the Space Rocket History Podcast. If you are financially able, please support the podcast by going to the homepage, spacerockethistory.com, and clicking on the orange Donate button or the Patreon link. Thanks.